All right, so tonight, or second part of tonight, I want to talk about biomaterials and nanomaterials, and that'll kind of get us prepped for next week's discussion. Okay, so biomaterials. So unlike other types of materials, biomaterials are classified not by their chemical composition, structure, or properties, but by their function. Okay, so what do I mean by that? What I mean is we've talked about different types like polymers. We've talked about composites, and biomaterials are all of these things. So instead of talking about the biomaterial in terms of what it's made out of, we typically talk about what it's designed to do. So a biomaterial, by definition, is a material that's been engineered for interaction with a living system, and that's direct interaction, right? So is your chair a biomaterial? No. Yes, it interacts with a living system because you sit in it. I grant you that. But I don't think anybody in this room would actually consider a chair to be a biomaterial, right? So really what we do is we extend the definition to materials that are in vivo. And what do we mean by in vivo? We mean within the body. Okay? So a good example of this is if I had a knee implant, I think we would all agree that a knee implant is a biomaterial. Right? I wear contact lenses. My contact lens is not considered to be a biomaterial in the truest sense of the word because it's not inside of my body. Right? That's even maybe the gray area. Would you consider your eyeglasses to be a biomaterial? I would argue, and I think most people would argue, that it's not a biomaterial. Right? It's glass. It does perform a function, but fundamentally, your glasses are serving no more of a purpose than the chair is. Right? It's interacting with your system. My contact is really the same. It's not inside my body, so we do not really consider that to be a biomaterial. Okay? So what are some things that we collectively might have to think about as concerns for biomaterials? What's that? Okay, way they react to your system. Very good. What else? Lifetime of the material, very good. What else? How do you get it in? You cut somebody open and stick it in. That's the easy part. Doctors, hey man, doctors are the slicers and dicers. We're the engineers, right? So, fundamentally, it goes down to biocompatibility, right? What do I mean by biocompatibility? Just what it says. How compatible is it with the system that you're using? Okay? What we mean by biocompatibility is the ability of the material to perform a specific function in the body without causing negative, or you'll sometimes hear deleterious, effects. What's the difference between a negative and a deleterious effect? What's that?
Is deleterious not always bad?
Deleterious generally, so negative means if I put it in and I like break out or I have reject it, right? Deleterious oftentimes, they're very interchangeable, but deleterious oftentimes will mean a prolonged type effect, whereas a negative type effect, deleterious of course is negative, right? But deleterious generally implies some sort of prolonged effect, like maybe we put something in and after a couple months it starts to dissolve or something like that, right? Okay? So a biocompatible material has to be capable of coexisting with living tissue without causing harm. They have to be robust against chemical attack and corrosion and must maintain their compatibility as they wear, right? One of the big things has been, over the last, 20 to 30 years, has been hip implants, right? We've got those down. We know how to stick them in, older people or even younger people who need them. But the problem is a lot of these were starting to wear out. And what's the problem? Let's say you're 60 years old, like my grandpa was when he got his hip replacement, and then he makes it 20, 25 years, which is fantastic, but now the thing starts to fall apart. What's one of the problems there, aside from the fact that it's starting to fall apart? Let's just go in and replace it, no big deal. What are we now doing? We're cutting open a significantly older, more frail individual to go in and replace it, right? So we improve that person's quality of life, but now we've been presented with an even bigger challenge. Cutting open and having a 60-year-old repair themselves versus cutting open and having a 90 to 95-year-old repair themselves are two significantly different items. And at that point, such as in my grandpa's case, he had to make the decision whether it was worth risking dying on the table or just not being able to walk for the rest of his life, right? Those are real decisions that people have to make, okay? So the physical impact of the material on the surrounding tissue is of great importance, okay? Not only must it be non-toxic, obviously it's pretty simple that we don't want to put something poisonous in someone's body, right? That one's very simple. But it also has to not provoke the body's own immune response, right? That's what we call rejection, okay? Because at best, rejection will cause the body to wall off the material, right? It'll form fat around it or something like that and essentially just make it a tumor, right? And a good tumor, right? Not a bad tumor. But it'll wall it off, make it ineffective. But if it causes an allergic response, you could kill the patient, okay? Do note that biocompatibility is not universal, which is what makes a lot of this so very tricky. A material suitable for one use may be rejected by the body in another application. Like let's say a hip implant, or let's stop using that one. Let's say we have a joint implant made out of like titanium or something. But we were to place that same exact material in some other part of the body, it may not be accepted the same because not all body tissues are the same and not all body functions are the same. Okay? So just because titanium's okay for use in your leg doesn't mean that you could necessarily put it in like your heart. Okay? Now titanium alloys are pretty much the go-to, or have been for a while. Metals are frequently used as substitutes for hard tissues, such as in joint replacements. And by hard tissues, what do I mean? Bone, right? Bone is a tissue. I do mean bone for hard tissue. Okay? However, most metals display limited biocompatibility and are not tolerated by the body in large quantities. So not only must a metallic in the body be strong, but it also has to actually cooperate with the body, right? Titanium alloys such as Ti6, aluminum 7, neodymium, Ti6Al7Nb is a high-strength Ti alloy developed specifically for use in vivo. This alloy contains roughly 6% aluminum, roughly 7% niobium, so I did say it wrong, yep, and has a typical density of about 4.2 compared to the average of 3.88 for the human bone. So it's a little heavier, but it's pretty compatible, but it also won't be rejected by the body largely. Okay? So although it has less strength, its biocompatibility is far superior. So instead of just sticking straight titanium in there, which by some patients can be rejected, what they've done is they've gone back and they've engineered an alloy that will be better. It will have less problems with deleterious tissue growth. So this becomes advantageous for use in other biomedical implant devices such as pacemakers, artificial hearts, and valve replacements. Right? And that's fundamentally what we've seen. That's what I was talking about already. Right? It was okay in the past to use just a basic titanium leg. But titanium itself was not as ideal for use in other cases. This specific alloy can be used largely in the body without problems. Now, why do we think that throwing different types of metals, right, and this is where we go into the materials engineering part of it, right? Why do we think that adding those different, alloying those different components matters? So let's think about 2 lectures ago. What starts happening to our crystal structures or our structures when we start adding different size components into our structure? What starts happening to it? It changes, and how does it change it? Could become more amorphous, yeah. But it can change the density, right? Because now instead of having all of our ping pong balls packed closely together, now we might have a bigger ping pong ball in there that makes them spread out a little. Maybe it's a little more dense. Maybe it does not, or maybe it does cause smooth surfaces, or maybe it causes rough surfaces, which makes it harder for certain things to grow on it, right? There's all sorts of options that we have to identify and then design our material to account for. Next, we have bioactive materials. So an important consideration in this is that living systems, as you guys know, are dynamic. Presents challenge and advantage. The obvious advantage is that the body heals itself, which is pretty awesome. The challenge on that is something that's okay today might not be okay tomorrow. Okay? So bioactive material are of great use because they can actually bond directly to living tissue, which allows it to become part of the body. Okay? So one of the ways that we can use something like this is, does anybody know what hydroxyapatite is? Hydroxyapatite is basically bone. Okay? So hard tissues such as bone and teeth are not uniformly solid, but they're natural composites composed of a mineral foam of calcium phosphate, proteins, and water. So hydroxyapatite, which is calcium 10, well, you see it there, right? But this is a complex biologic ceramic that acts as the structural component in hard tissues. So we essentially have our bone, which is proteins, and in it is these hard rocks. So a very poor example would be something akin to concrete, right? Is essentially what our bones are. Okay? So approximately 70% of your bone is some form of this hydroxyapatite. Dentin is roughly 45%, and enamel is nearly 95%. Enamel being on your teeth, right? That's why the outside of your teeth are harder. Okay? So what we can do is these bones, right? Bones are considered to be a two-phase composite material. We have hydroxyapatite as one phase, and then we have collagen polymer as the other. So like I said, it's essentially a concrete of sorts, right? We have these long polymers that help our bone, which is good. Why is that good that we have polymer in our bone? Does it strengthen it? What's it? Makes it stronger, or does it make it more flexible, right? Because let's think about it. So right now we're going back to a couple lectures ago talking about our ceramics. What happens if we were to drop, so hydroxyapatite is a ceramic. So if our bones were purely ceramic, what would happen if we jumped off like anything? We'd shatter, right? Right, so your bone allows, the fact that your bone is both, the fact your bone is a composite allows it to perform both functions. It gives you a little bit of flexibility, gives you a little bit of pull, but it gives you a lot of strength in the ceramic itself. Okay, so where I was going on the living tissue portion, what they've actually started doing is on some leg implants, they've actually started coating certain implants with hydroxyapatite mesh, and then they put that right onto the bone and screw it into the bone. And what starts to happen is, because this is a porous mesh of hydroxyapatite, which is essentially bone, your bone actually grows into it and essentially fuses and becomes part of you, right, for lack of a better term. As opposed to being something that's been screwed onto you and stays there, your body can actually grow in and accept the joint because it actually just like grows into it. Does that make sense? So that's what we mean by bioactive. That's how we can take advantage of bioactive materials. Okay? So our tooth also, just for example, we were talking about dentin sorry, what's the stuff on the outside? Remind me. Enamel, right? The enamel on the top is very hard. Your dentin in here is also a composite, but if you look at the tooth on the whole from a cross section, it's just one big composite material. Okay? So bone strength, and this is what we were talking about with it being a polymer. Bone strength depends largely on the direction of loading. Your bones are very good in compression, right? Again, that's like if you were to jump off that table onto the floor, you'd probably be able to handle that pretty well without breaking anything, right? What's going to break or what's going to go first is like an ankle or something like that, right? Your bones are very weak, however, in shear. Why do we think that is? Remind me, what shear? That's when things are going against each other, right? Why are our bones weak in shear, do we think? Why do you think, Medicine? You don't know why they're weak in shear? All right, which direction are our polymers going? Mostly long ways, right? For give or take, right? Just like wood. Yeah. And again, the pure material engineers will jump on me for that, right? It's not like wood, but I know what you're going for, and yes. Okay. So the rate of loading is also important, which makes sense. Bone is what we call viscoelastic. Remember we were talking about our silly putty last week? What happens if I slowly stretch my silly putty? It stretches and stays together. What happens if I take my silly putty and I go like that? It breaks, right? Your bone's the exact same, right? If we were to suddenly run into a wall or something like that, you're going to be a lot more likely to break a bone. Or if you were to suddenly fall, you would be a lot more likely to break a bone than if you were to slowly lift something with, like, let's use an example of if I were to try to lift this desk with my leg, I'd probably be able to lift the desk and have no problem, right? But what would happen if I were to kick the desk really fast? Probably would not end well, right? It's the same type of idea. Okay? Then of course, bone density changes with age, disease, nutrition. That's why you have to eat well, and lack of use, so don't be lazy. Young bone, so you guys, is more ductile and less brittle than older bone. So more strain is allowed in young bone, which is why athletes eventually can't be athletes anymore. Okay? So let's start thinking about this in terms of breaking a bone. Okay? So failure mechanism for bone loaded in tension is mainly debonding at the cement lines. And this is what's called a transverse fracture. So this is if for some reason you were to get your leg pulled apart, your leg would basically just break nice and simple like that. Okay? If your bone was to go under some sort of compression, what we typically see is an oblique fracture, like that. And that's where it's a lot nastier, right? That's where bones can all of a sudden start poking out of your skin, right? Okay? And generally, this is about at 30 degrees. Okay, so those are the raw drawings. So if we go into this drawing, and this is where you start getting in real trouble, right? So in bone bending, there's a combination of compression and tension. Remember, bending, depending on which side, you have elongation on the top and you have compression on the bottom. Remind me again which one of those usually breaks first? Tension is usually the one that breaks, right? And that's why we talked about tensile testing and all that, is tension is usually the one that fails first. Okay? So in this case, on our bone, or now remember, every force is equal and opposite, right? So if I have a force pressing here, I have to have a force pushing back here. So what literally starts to happen to our bone is it starts to break like this guy. So you get a relatively good snap. However, in compression and bending at the same time, so this is just bending, but in compression and bending, which is usually what's going to happen if you were to, like, let's say, jump off a roof or something like that, right? You're not just going to land flat down, and you're not just certainly going to bend your leg. It's going to be both. What you get is a really nasty one, and this is the worst one, called the butterfly segment. Because what happens is you start to bend, but when you also have the compression, what happens is you form this little chit here in the back, and then what happens to that little chit? It breaks off, right? If you're lucky, maybe it stays on. But you start to get theirs on the fracture, and then you have this nasty looking fracture right there. All right, and this all has to do with bone mechanics. Right, so this one's not in your book, but a spiral fracture, I'm sure you guys have heard of that one, occurs when a bone breaks under torsion. Select the spiral fraction below. Happens in sports all the time when, like, you plant a foot and then you get hit from that side. You lacrosse players, you football players, soccer players a lot will see spiral fractures. Skiing, oh my goodness, skiing. When the one ski goes this way and Andrew's head goes that way. Yeah. All right, so which one of these is a spiral fracture? Do we agree on the last one? Why is it the last one? Because it's the only one that doesn't look like what we've seen already? All right, fair enough. All right, but yeah, so what happens is you have that line, but you're under torsion. So what happens? You're actually starting to get, what is torsion a form of? Shear. Very good. Yes, it is twisting, but it's a twisting form of shear, right? So what happens is your bone literally starts to go, right? All right. So that's hopefully not everybody's all grossed out and heebie-jeebied right now thinking about how their bones are going to break, but your body is nothing more than materials, right? So for those of you who want to go into biomaterials, you need to think about it. All right, now, what is a nanomaterial? It's small? Okay, lecture over. Done. All right. Why? Yes, you're correct. Nanomaterials are really small. Does anybody know what the scale of nano is? 10 to the negative 9. Andrew for the win. Yep. All right. So nano. All right. So, and remember, I did my PhD thesis in nano, so nanomaterials, so all over it. But, all right, so nanomaterials, materials that measure less than 100 nanometers in less than one direction. So it's kind of a trick. It's not actually a nanometer, but they're in the nano range, right? And the reason it's less than 100 is because that's once you get out of microns, right? So particle is less than 100 nanometers in all dimensions is called a nanoparticle. These measure only a few nanometers in diameter and can be made up of only a handful of atoms. Why is that important? Let me ask you this. If I have a big bulk of material, okay, how much surface area, or I should say, what fraction of my soccer ball is the surface? The answer is not very many, right? If I were to weigh the number of atoms on the surface of a soccer ball versus the weight of the whole soccer ball, it's negligible. The reason that the surface atoms are important is because they're literally bound different within the material from an atomic structure standpoint than any other thing, right? Something on the inside is bound equally in all directions. But something on the surface still has to be electrically neutral, and it still has to be bound, but those angles have to be at a different angle. Why? Because there's nothing in the other direction, right? So what you see is this effect where surface particles, or the surface atoms, the surface particles, are in a different state. And they are themselves very different. What happens as you start to shrink the size scale is that eventually the surface particles become more of the surface atoms become more of the particle than the bulk do. And all of a sudden, at some point in the nano range, nanomaterials start to behave very differently than their bulk counterparts because it's not bulk material anymore, it's all surface atoms, or largely surface atoms, right? Some of these nanoparticles may only have 17, 18, 20 atoms in them, right? When you think about most of those being on the surface and being bound in a different way, your material, like you could have a steel nanoparticle that no longer looks like steel at all, right? Okay? So because of this factor, materials in the nanoscale can display very unique electronic, magnetic, mechanical, optical, and thermal properties. Okay, so surface volume effect, let's cut to the, before I'll cut the light so you guys can get the full effect of this next one. Okay? And we already talked about this, but let's talk first about quantum dots. So that looks pretty and it looks cool, but what's super cool about this, the particles in each one of those vials are exactly the same. They're exactly the same composition. Okay, so in this case, I believe these are cadmium selenide, but quantum dots are incredibly small single crystal nanoparticles, and that's important, made of semiconducting materials. Particles are typically only between 2 and 10 nanometers in diameter, meaning that quantum dots are literally only a few atoms across and comprised of only a few hundred to a few thousand atoms. Okay? So in this case, what we start to see, and let's remember our picture here. I'm going to turn the lights back on. What we start to see is fluorescence. So we all know that if you guys give an atom energy, it becomes excited, right? What happens when we shoot something with light? What can happen to some of the electrons? They can jump shells, right? And what happens when they fall back? They have to emit light or energy of some sort, right, to fall back. Okay? So what happens is as that electron falls back, it emits emits energy equal to the energy absorbed in the form of light. Okay? Different atomic species require different amounts of energy to become excited, and thus the color of emitted light varies for each element. And this is why potassium burns purple, right? You guys have certainly done this in chemistry class where certain different colors, like maybe you had to identify, that's usually one they do in chemistry class, right? They'll give you an unknown sample and they'll make you identify it. One of the things you can do is burn it and be like, oh, it burned green, so it's probably like a copper or something like that, right? Right, so we understand that different elements burn different colors. But quantum dots behave in a similar manner, but with a twist. Instead of emitting light based on the type of atom it's made out of, the color emitted by the quantum dot is directly related to its size. Why would that be? Does anybody have any idea? Why? So it's the amount that it requires to excite an electron. But why would that change based on, even if all of my particles, so let's go back here. All of these guys are made out of the exact same material. So why in the heck are they different colors? Right, and why does that matter? So let's go back to just what we were talking about. If my particles are different sizes, the ratio of surface to volume is different for each one of those, right? So the way that things are bound, the electronic structure of those surface versus the bulk changes the entire band gap of the entire structure. Okay? So what we end up seeing is that over decreasing size, now somebody remind me real quick, high intensity light is what color? White. All right, so let me ask the question a different way. Is red a higher wavelength? Or is blue a higher wavelength? Okay, so now remind me, is high wavelength high energy? Very good, right? So what we see is decreasing size will change the color. The lower energy colors will be at the larger sizes. The higher energy colors will be at the lower sizes. So if we go back to this one, of these guys, which one of these do you expect to be the larger dots? The reds, right? And I believe they're in decreasing sizes, or yeah, decreasing sizes here from left to right. But the reds on the far side, your larger ones, are going to have less energy when excited. Or when they fall back, that is, not when excited, when they fall back. And the ones on the right are going to have higher energies. Okay? And that's actually what my PhD project was, something very similar. I could make silicon nanoparticles of different sizes and they would fluoresce differently. All right, we also have, who's heard of carbon nanotubes? Yeah, probably a lot of people, right? So carbon nanotubes are really cool. They're cylindrical carbon molecules with extraordinary strength and very unique electrical and thermal properties. And the way they work is it's essentially a graphite sheet that's been rolled up. So it's a hollow tube that's very, very, very small, sometimes only several atoms across. In fact, or not several, only several atoms across, right? So this, let me turn off the light again, just so you can see it. As we look closely there, you can actually see the atomic lines. So this TEM, transmission electron microscope, reveals the multi-wall nature of a carbon nanotube. You can see a 10 nanometer inner diameter with 9 concentric walls and a clear inner channel. Okay? What you're literally seeing there are rows of silicon atoms. It's a pretty great picture, which is of course why they got printed in a journal, right? But all right, next we have nanowires, which are extremely thin structures that have a width measured in only nanometers. Just like conventional wires, they're composed of metals like copper, aluminum, silver. Aluminum ones have actually tended to be pretty good. Or you can have semiconductors such as silicon and germanium. And they work the same as a normal wire, except for one thing. They're super, super, super small. Right? What do you think we would use nanowires for? So one of the applications that people are using nanowires for is, again, what do they have? What do we think? Let me back up. If I have a whole bunch of nanowires, what do I have a whole bunch of? Surface area. So what a lot of people are using, because each wire has an external thing, or has an outside. So what we've done is we've increased our surface area. So one of the things that we use nanowires for is as detectors. Right? They can very easily detect, because think about it, these nanowires, you can literally run a current through them at a very low level, of course, right? But if you can run a current through them, and if you attach some other form, like say a protein that you're looking for or something like that, what will it do to the conductivity, or what will it do to the current going through your detector? It'll change, and you can say my current just changed, I've detected what I'm looking for, right? So there's a lot of applications for these in detectors. This technology is probably a long ways away from actually being used in computers, and by a long ways away, like probably never. But that's being the way that these matrix, because a lot of like these wires aren't 20 feet long, right? We're talking about a high density lot of little nanowires. A lot of surface area present. You can grow it on like a mesh, you can grow it in something like that and use it as a detector in your system, right? There's a lot of medical applications, a lot of potential medical applications for this as well. Okay? All right, so we talked about nano. Does anybody have any other questions? I think we're all set up for next week. Okay, so we're going to come in next week right on time. We're going to talk about surfactants real quick, which will give us a nice primer for cell walls and drug delivery. Then we're going to talk about cancer fighting techniques and engineering cancer. And we're going to talk about drug delivery at the end. And that'll be it. But I want you guys to remember some of the nano stuff and some of the biomaterial stuff we talked about, because that's why I was prepping you for that. Okay, do I have any other questions? Any other clarifications? Okay, thank you guys. I will see you next week.